Alright, in this video, we're going to go over the basics of nuclear chemistry. We're going to see what nuclear reactions are, how they're different from chemical reactions, and we're going to learn about the different types of nuclear reactions we can have. So by the end of this video, you should be familiar with all these vocabulary terms. So we have the law of conservation of matter, chemical reactions, nuclear reactions, the strong nuclear force, fusion reactions, and fission reactions. Now, when we're talking about chemistry in general, we always have to keep this one idea in mind. This is one of the basic laws of nature, and it's called the law of conservation of matter. It states that matter cannot be created or destroyed. What this means for us is that we can't make new matter and we can't permanently get rid of it. Whenever we do any chemical process, we're only changing the matter in some form or fashion. On chemical reactions, what this means is that our atoms and our elements don't change. We only change how they're connected, maybe how they're paired. They will go to other places, but they will not be destroyed. We will never get rid of it permanently, and we can't make new atoms. So now what this looks like in an example of a chemical reaction. We'll talk more about these in Unit 5 and Unit 6, but for now, you should know that when we have this set up, we have the hydrolysis of water. Now, what these arrows show us is that it is a chemical change, it is a chemical reaction we're going through. And it's basically splitting up our reaction into two sides. We have a left and a right side. You can think of it as a before and after picture on this. If we focus on the atoms and the elements that we have. So here on the before side, we have two molecules of H2O. You might recognize this as being a water molecule. So when we have this in the hydrolysis of water, we start with two water molecules. If you go through and you count the individual atoms, you'll see that in the red we have one oxygen atom and two oxygen atoms. So I can go ahead and list that one out. And this is my before side. In the after side, after I've performed the chemical reaction, I can count my products, see what I have left, and you can see I still have one and two oxygen atoms. Right, so you can see that on the left and the right sides, the before and the after, you start with two atoms of oxygen and you end up with the same two atoms of oxygen. You haven't made any new oxygen, you haven't lost any oxygen. You've just arranged it a little bit differently. All right, same thing for the white hydrogen atoms. If you start on the before side and you count them out, 1, 2, 3, and 4, you have four hydrogen atoms. In the after side, if you count 1, 2, 3, and 4, again, you have the same four hydrogen atoms that you started with. They're just connected differently. They're paired with different things than what they started with. Now, when it comes to nuclear reactions, we're still playing by the same rules, right? Still, the law of conservation of matter applies. We can't make new matter, we can't get rid of matter, we can only change it in small ways. And so now what this looks like in a nuclear reaction is that we're actually changing the nuclei of the atoms, but the subatomic particles don't change. So it's still that same idea that you get out what you put in. So let's go ahead and see this. All right, so this would be an example of a nuclear reaction. So what's going on here is that we're starting with a very large atom of uranium, right? And so we are taking a very small neutron and we are shooting it straight into that uranium atom. You can think of it as being a bullet that is going to split the atom right down the middle. And then you can see that in this middle stage, we have a very unstable nucleus. It starts to fall apart and it breaks apart into two different pieces. So we have a krypton atom up here and a barium atom down here. So now what's going on? You should remember from the last section that it's the number of protons in the nucleus that tells you what element you have. So what's going on in this is that we started with an atom of uranium with 92 protons, and in our products we have two different elements. We have krypton with 36 protons, and we have barium with 56 protons. So now this is different from the chemical reaction because we have changed the elements that we started with. But if you go through and you zoom in, you count each individual, the subatomic particles, protons and neutrons, you'll see that we haven't actually lost any of them. So let's go ahead and take account of those. So if we start here with our before side, before we get to these arrows, we have a atom of uranium with a mass of 235. We'll just focus on the masses for these because we don't have to say which are protons, which are neutrons. We just need to know what the mass of these are. So again, we have an atom of uranium with 235 atomic mass units, and we have a neutron with just one atomic mass unit. If you combine those, just 1 plus 235, you see that we have a total mass of 236 between these two atoms. Now, this intermediate stage, they combine briefly for a second before they fall apart, but you see that same number, we have a total of 236 mass units. And then after they fall apart, you'll see that we have two atoms with two different masses, 92 and 141, as well as three neutrons that get ejected. They each have one atomic mass unit. So you can count through all of those. So if you take 92 from the krypton, you can take 141 from barium, and you can take the three individual neutrons. If you add it all together, you still get that same number of 236. So it follows that same idea that we haven't lost any matter. We've just changed where it is, where it's paired, and what atoms are contained. But again, you get out what you put in. We haven't lost any of our matter. It's still all accounted here for. And in the process, we've released a lot of energy. And so, in this process of the nuclear reaction that we had, we started with a very large nucleus of an atom, and we split it into two smaller pieces. And in that process, we've also released a lot of energy. And where that energy comes from is from the strong nuclear force of atoms. So, for the strong nuclear force, it is a fundamental force of physics. There's only four of them that really govern everything physical around us. And specifically for the strong nuclear force, it is the one that holds our atoms together. It's what keeps them from flying apart, and it's what separates them from other atoms nearby. All right, so let's put that amount of energy into a little bit of perspective, because it's very easy to just talk about, yes, we release energy, and we can use that energy for stuff, but how much energy are we really making in this process? Well, just to put that into perspective a little bit, is that if you were to take a beach ball, and take an amount of oxygen the size of a beach ball, medium-sized beach ball, normal-sized beach ball, and say that it had about 16 grams of oxygen. If you could take every atomic nucleus of those 16 grams of oxygen and release all of the energy in the strong nuclear force, you would make about as much energy as 420,000 kilograms of coal. Yeah, that's right. I said 420,000 kilograms. It's not a typo. It is a tremendous amount of energy that you're releasing for a very little amount of starting materials. And it's exactly for this reason why something like a nuclear weapon, it can be very small, but it can have a very large destructive power because you are releasing a ton of energy from that strong nuclear force. Right, now, let's move on to the different types of nuclear reactions that we can have. So there's only two types of nuclear reactions that we need to know, and they are the fusion and fission reactions. And so now for the fusion reaction, this one we're taking two small atoms and we are joining them together to make one larger atom. So in this example, you can see that you have tritium and deuterium. These are two heavy versions of hydrogen atoms. And you can see that they each have one proton in red here. So one proton for tritium, one proton for deuterium. They're both types of hydrogen. And through the process of fusion, you can see that over here, we're making a bigger atom than what we started with. We have helium with two protons in the nucleus, and we are also getting a neutron as leftover products. And now this type of reaction is the most powerful type of nuclear reaction. And really, the only place that we can see this type of reaction happening is in the cores of stars. So, this is what powers all the stars in our galaxy, all the stars in the universe, and our very own sun are powered by this very reaction. It's what gives the sun all of its energy, all the light and heat that it puts out, and it's what makes life in this planet possible at all. It's this fusion reaction, and the conditions for this are so extreme that again we can only find it in the cores of stars is where we can achieve these type of fusion reactions. And the other type of nuclear reaction is kind of the opposite of this one. It's the fission reaction, and in this one, we're not joining atoms to make bigger atoms. We're actually taking large atoms and we are splitting them into smaller pieces. So this is the example that we saw before with the splitting of the uranium atom into smaller pieces. All right, now this type of reaction, it's not as powerful as the fusion reaction, but it's a lot more manageable. It's a lot easier to control, and it's the same type of reaction that we use in our nuclear power plants. All right, so that's all of the basic information we have for nuclear chemistry. That's all that we're going to get into for the nitty gritty details. Now, after this, we will be talking about nuclear energy and just how it works. It's a very basic principle, even though the actual details can be very complicated. And so, again, it's a very powerful technology that we can use, and so just like any powerful tool, it can be used for good or it can be used for evil too. So now there's definitely some benefits to it and there are drawbacks to it. So I have this series of videos as well for you to watch. Make sure that you take notes on this, and all this information we will be using next week for some discussions that I have planned. So I'll give you more details about those discussions next week when we're actually looking to get started on it. But for now, I just want you to be informed. I want you to learn what the benefits and drawbacks of nuclear energy are, how it all works. So make sure that you take time to watch these videos, take notes on it so you can bring them back next week. And if you need any of my help, make sure that you ask.